Hello, my friends. Welcome to a new unit on energy, power, and work, not necessarily in that order. Um, as a little introductory activity, this will be something you can spend a few minutes on your own. Sorry, I spilled a lot of water on the floor. I'd like you to have a look at this, and by this I mean this. That is an animation of a steam engine. All right, and this steam engine brings, here's a red arrow that goes in like that, brings steam, hot steam into this through this valve, and it's allowed, depending on the position of this little sliding deal, it's allowed to sneak in here, and when it sneaks in here, it pushes that piston over, which then pushes this other piston, which is connected to a cam here, which makes this wheel turn. And then there's a belt attached to this wheel that maybe is connected to something else somewhere else. And can do some other stuff. And, well, you notice that once that steam has done its job of pushing this piston over, well, it cools down, and then that cooled steam is allowed to exhaust out of there. All right. The bottom line is this is a pretty complex machine. There are simple machines, which you've heard of. We can talk about those tomorrow. This is a pretty complex machine. But what all machines do is they convert one kind of energy into other kinds of energy. All right? So what I want you to think about is what kinds of energy transformations occur in this steam engine. And I'm going to bring you all the way back to where this thing starts, not even in this animation, because a steam engine typically starts with something like coal, all right? And so the question is, well, what kinds of energy are there that present in the coal that are transformed into different kinds of energy, and what does that energy do, and how does that make something else, some other energy transformation happen? So the idea is to say, well, the coal maybe has something like potential energy stored in chemical bonds, right? And, well, what does that do? Well, you burn the coal, and that turns into maybe something like, well, what kind of energy is that when you burn stuff? And, all right, well, that kind of energy then is used to do this, and that makes this. So you get what I'm saying? I want you to end up talking about or trying to mention lots of different kinds of energy and where these transformations and how, through what mechanisms, maybe, these energy transformations take place. Okay? At the end of the day, right, we get something moving here, right? Well, moving in a circle, and here's things moving like this, and so there's all sorts of different kinds of energy that maybe, I hear some of you saying, but we're just starting energy. How should I know any of this? Well, you already have some knowledge. I guarantee it. I know you do. So I want you to see if we can get at that knowledge, okay? Okay, now, we're going to talk specifically about, right now, about two kinds of energy. Really, well, the one kind of energy that we're going to focus on in this unit is what's called mechanical energy. All right, mechanical energy has two main components, potential energy and kinetic energy. All right, and potential energy actually has several components, but we're going to deal with what I should, so I should say kind of 1A, this is what we'll call gravitational potential energy, or GPE we'll call it. So, which of these bowling balls do you reckon has more gravitational potential energy? The one lower down by the floor or the one high up in the air? Well, take your pick. What do you think? It's that one. Yep, you're right. It's the one higher up in the air. And why is that? Well, GPE is proportional to height. Right, this has to do with gravitational stuff, and the higher things are up, really the farther away this object is from the center of the Earth, because we say that it has gravitational potential energy with respect to the Earth. All right. So yeah, the farther it is from the Earth's surface, or in our case, we'll just call it the higher it is above height 0, the more energy it has. All right. This is kind of an energy of position. Now, which of these objects, I know it says kinetic energy up here, but we're still talking about gravitational potential energy in this slide. Which of these things has more gravitational potential energy, the bowling ball or the tennis ball held at equal heights above the ground? Well, take your guess. Going once, going twice. It's, oh yeah, bowling ball. And GPE, proportional to mass. Fair enough? Good. Now it says PEG. That's one way to do it. We'll do GPE. So we need proportional to mass, proportional to height, and, well, a G goes in there because this is, well, what we call gravitational potential energy. Okay? Now, the units. Well, it looks like it's got to be kilograms for mass, meters per second squared for G, and meters for H. So that's kilogram meters squared per second squared. That's one way to say it. Or we could say that a kilogram meter per second squared is Newton times this meter. And a Newton meter is what we call a joule, or capital J. Yeah, somebody said before, we've seen these units before. Come on back with it. What are those units of also, oddly enough? So yeah, there's the units of gravitational potential energy. The joule. All right, 2.5 kilogram block is lifted 1.5 meters above the ground. What's its potential energy, what we call relative to the floor? Well, G, P, E equals M, G, H, G, P, E equals mg, I'll call 250 newtons, times H, 1.5 meters. Ding, ding, ding. Okay. Oh, right away into a little doozy, a miniature doozy here. Express the pendulum bobs. This is Bob. That's the Bob. GPE relative to the bottom of the swing in terms of all those things. Well, the question is, if this is the bottom of the swing, and here's this angle, you got to figure out for me, if this height down here is what we call height 0, the question is here, what's this H? Because we're going to say that GPE is mgh. Give me an expression when you come back in tomorrow for H in terms of all that stuff. Okay? Little job. Job 1. Oh, job 1. Job 2. Onward. Yeah. Yeah, notice, if I write a good question, I'm always going to say, what's the potential energy relative to somewhere? If I'll show you tomorrow, but if I just say, hey, what's this object's gravitational potential energy? That is an unanswerable question. All right, unless you or me, one of us, has to define where we're calling 0. And notice the bold part. It's small. You probably can't see it. It says, in lots of questions, you pick the 0 height that's most convenient for you. Okay? Okay, kinetic energy. Which has more kinetic energy? A rolling tennis ball or a rolling bowling ball? And rolling is a whole thing that I should not have introduced here, because there's, well, we're talking here about translational, not rotational. Things that roll have rotational potential, or sorry, kinetic energy that we're not talking about. So let's assume that these are a tennis ball and a bowling ball hurtling through the vacuum of space in near zero gravity, not rolling at all, they're just moving. Which one has more kinetic energy? Well, it's the bowling ball. And Ke is proportional to mass. Okay? Which has more kinetic energy? The fast tennis ball or the slow one? Well, it's the fast one. Because kinetic energy is energy of motion. And kinetic energy is proportional to velocity. Was that right? Yeah, I think that's right. So Ke, well, proportional to mass, proportional to velocity. Now it's an energy, just like potential energy, so that means it has to be measured in joules. Well, a joule is a Newton meter, or a kilogram meter per second squared times a meter. Well, here's the kilogram part. Now we need kilogram meters squared per second squared. That almost looks like V if we were to square V. Yeah, so let's square V. That means that kinetic energy is not proportional to V, it's proportional to V squared. And also, we throw a 1/2 in the front. So there's an equation for kinetic energy, 1/2 mv squared. All right, pitcher throws a 350-gram baseball at 35 meters per second. What's the kinetic energy of the ball? Ke, 1/2 mv squared. Whoops, that's not true. Meters per second squared. Oh boy, that's like a third. I don't know. I don't know what this is. This is somewhere like over 1,000. So this is like maybe like 200 or so, on the order of 200 joules? Question mark. I don't have a calculator handy. Aha! A 5-gram bullet has the same kinetic energy as a 5-kilogram bowling ball, moving at 8.5 meters per second. What's the bullet's speed? So sure, just because a bullet's really small, or just because a bowling ball is relatively slow, doesn't mean they can't have the same kinetic energy. So I'm going to say that, let's call the bullet number 1 and the bowling ball number 2. It says that their kinetic energies are equal. 1/2 m1 v1 squared is 1/2 m2 v2 squared. What's the bullet's speed? v1 is m2 v2 squared over m1. Right? Or it's really the so whatever that is. Okay? You can solve. 3. Good? Okay. Now, let's look at what we call energy transformations. Now here's that same 2.5 kilogram block held 15 meters above the ground. Calculate its total mechanical energy. Well, by definition, mechanical energy is the sum of gravitational potential energy and kinetic energy. But notice this is held, no kinetic energy. Look back, if you must, but we said that, remember that from a couple slides ago? So this thing has a mechanical energy of 375 joules. I'm getting emails, people. Now we release the block and it falls to the ground. Let's find the block's kinetic energy just before it hits the ground. Well, that means we need to find a velocity just before it hits the ground. It goes from here to here. Right here it's moving at some speed vf. Sorry, we just call it v, right? Well, yeah, sure. Yeah, so we know that v naught is 0. We know that delta x is, 15 meters. And we want to know v. Well, v is going to be v naught plus 2g delta x delta y. Delta x, same thing. This goes. So v is the square root. Well, you know what? If we want the final, I wish I had said this, find the blocks, not kinetic, but mechanical. Right, we found its mechanical energy before. Let's find its mechanical energy now. So again, that's gravitational potential plus kinetic. Let me move some of this and kind of start over a little more intelligently. So now we're saying, again, mechanical energy is GPE plus KE. Well, now it's just before it hits the ground. Let's get rid of it. Let's get rid of that and say it's at height 0. An infinitely small height above 0, something. Infinitely small height. Yeah, sure. So the mechanical energy now is equal to its kinetic energy, and so that's going to be ½ mv squared. Well, notice that we said that v, we have that expression for v squared, right? V squared is v naught squared plus 2g, I'll call it delta y, how about that? So we can say that the KE now is ½ m2g, well, delta y, isn't that the same thing as h? Huh. 1/2 and 2 divide away. Well, look at that. The KE ends up being mgh. Now, it's definitely equal to 1/2 mv squared, but notice what 1/2 mv squared turns into. And in this instant, its mechanical energy ends up being 375 joules. Coincidence? I think not. So what can you conclude? This thing starts with a certain amount of mechanical energy, 375 joules. It ends later with the same amount of mechanical energy. Homework 4. At halfway up, find its total mechanical energy. Not find me, I'm right here. Just find the mechanical energy at height h equals h over 2. Or just at h over 2. It's going to be moving. Its speed ain't v over 2, though. Find its speed. Once you've done that, you got to do that now. You got to find yourself that mechanical energy. And then, let's conclude. So if you haven't found that energy yet, do so now. Welcome back. Hopefully you can conclude that, well, as long as, notice, we neglect air resistance, friction, and somebody accidentally sneezing on that ball, we can say here that energy doesn't go anywhere, but it's transformed from one kind to another. And that's called conservation of mechanical energy. Now, I should dress this up because I'm going to dress it up like this. In the absence of non-conservative forces, mechanical energy is conserved. Even with what we call non-conservative forces, like air resistance, total energy is still conserved. But we have to neglect the air resistances and the frictions of the world to conserve what we call mechanical energy. All right? Here's a problem. It's the classic. There's kind of two classic conservation of mechanical energy problems. One of them is a pendulum, like this one, and another one's a roller coaster. But here's the pendulum one. All right, and we're going to use the idea that mechanical energy is conserved. Initial mechanical energy equals final mechanical energy, as long as we neglect friction. All right, now initial mechanical energy is GPE. Final mechanical energy is GPE plus KE, of course. GPE final, KE final. So here we go from where we used to say, like, initial, we'll call it naught, and final, we'll just call it nothing. Now we just use I's and F's. It's the more standard way to do it. What are you going to do? In a typical conservation of energy problem, what you can do is say, well, do all of these stay? Any of them go away? Oh, look. Released from rest. See ya. Is it at height 0? Nope. Is it at height 0? Nope. Is it moving? Yep. So we got to keep those parts. And now we can substitute and say mgh initial equals mgh final plus 1/2 mv final squared. And the masses go away. And we want the velocity at the lowest point. That's this final velocity. So let's see, that's gh initial minus gh final is 1/2 v final squared, or that's 2 gh initial minus gh final equals vf squared, or that's 2 g h initial minus h final equals vf squared. Or, well, that's 2g delta y, right? I'll just leave it like it was. It's really negative delta y. It's okay. All right, because delta y, or delta h is really h final minus h initial, so this is the opposite of that. No big deal. Okay, so that's whatever it is, right? We have the mass doesn't matter. We have g's 10. Let's see, that's 1.15 meters is h initial minus h final, right? So I don't know what the square root of whatever that number is, but you can find vf. And yeah, it boils down to kinematics. All right, so I hear you saying, can I just use kinematics? Well, sometimes. But when we make these problems harder, you can't. So I would recommend against, well, and I will say this also, that when we test you on your understanding and ability to use energy concepts, you have to use energy concepts if you want full credit. And this is a good way to start. Now, look at the same problem. Remember, we said you, the savvy physicist you are, get to choose a convenient zero height if you want to. So is there a convenient zero height you can pick? Well, this is homework number 5, or 6, or 7, I don't know. Do the same problem, get the same answer that you'd get here by doing this work. Do the same, get the same answer, but make your job a little easier by picking a convenient zero height. Okay? Boo, work. All right, folks? That's it. I don't know how long this video is. It feels a little long. So plenty to do for tomorrow. Good full block to attack it with. So I'll see you then. Bye-bye.